Hello everyone, we're going to discuss today Chapter 10. I apologize in advance that this is going to be somewhat of a long lecture as far as these video lectures go, but the good news is it is the only one dealing with Chapter 10. So what is on the docket then for Chapter 10? Basically, we're going to be discussing projectile motion and satellite motion. And in the mix there, we're going to also touch on the motion of the planets and also escape speed. For a little review, remember when we were talking way at the beginning of the semester about free fall. Free fall was this idea that if you drop an object, say, for example, off of the Leaning Tower of Pisa, then it will be accelerated due to the force of gravity. And this is again assuming the only force acting on the object is gravity. And it will be accelerated at a rate of approximately 10 meters per second squared. The actual value is about 9.8, but we've been approximating that as close to 10 throughout the semester. So whenever you let go of the object, it will travel at first a shorter distance and then an increasingly longer distance as time goes on because of this acceleration. Okay, so if you were going to take a picture of where it is, where the object is located at each second, you would see that the spacing is not even. From time equal to 0 to time equal to 1 second, you would have a smaller spacing than the spacing between time equal to 1 second and time equal to 2 seconds, and if it were to continue on, the spacing would become increasingly larger under the influence of this acceleration due to gravity. Now, contrasting that with an object moving at a constant speed, we also discussed this formula where speed is simply your distance divided by time if you are not accelerating. So a simple example of that would be if you were rolling a ball across a horizontal surface, and if that surface were sufficiently friction-free that you could ignore friction, then if you did the same thing and took a picture of the position of the ball every second, you would, instead of seeing that uneven spacing, you would see an even spacing because it's traveling at a constant rate of speed. It's not being accelerated as it moves in this horizontal manner. So the subject of Chapter 10 being projectile motion is where we basically combine these two elements together. Projectile motion is essentially a combination of a constant horizontal component to your velocity, like what we show here with the even spacing, and an accelerating vertical component under the influence of gravity, where you have this uneven spacing of the position as a function of time because it's being accelerated downward. Okay, so if you combine this horizontal and this vertical aspect, if you didn't have gravity, you would just, if you tossed an object, say horizontally, you would just see this even spacing like is depicted here, even if you didn't have this surface here. If there were no gravity and you just threw an object horizontally, it would just keep going as inertia would demand at that speed, at a constant rate of speed horizontally. But with gravity, it doesn't affect this horizontal component at all, but it does affect the vertical component and accelerates the object downward. So if this is my vertical component and this is my horizontal component, then you can see these two aspects combined to give you this sort of curved path or curved trajectory. So we're going to define a projectile as any object that is moving under the influence of gravity and kind of continuing on that path, and it's really only gravity that's acting. Typically it's characterized by this curved sort of trajectory. Okay, and so you can do this thought experiment. If you did not have gravity and you rolled a ball off the end of a table, it would just continue in this horizontal manner. If you simply hold the ball at the edge of the table and drop it straight down, you have this. But in the real world, there is gravity, so if I roll the ball off the edge of the table, instead of dropping it, I will get some curved path, which is really just a combination of these two components, vertical and horizontal. Now, projectiles can also be launched with both a horizontal and a vertical component. It's not as though I need to choose one or the other. I might launch a projectile at some angle that has some horizontal velocity and some vertical velocity initially. And when I do that, what I'll see is some sort of parabolic trajectory unfold. But what's important to remember is that vertical does not affect horizontal. The horizontal component remains the same throughout this path that the projectile is taking. The vertical component is always going to be under the influence of gravity, though, and it is being accelerated. So here's a parabolic trajectory here of some projectile that's been launched with both an initial horizontal and initial vertical component. Now, it's also important to mention that what's shown here with a parabola is ignoring any effect of air resistance. In the real world, it's not quite a parabolic trajectory, but we're going to, for simplicity, ignore that and just look at a world in which we did not have to worry about air friction. Okay, so with that caveat in mind, then let's take a look at these vectors. The blue vectors that you're seeing at each point in time are depicting the velocity, both horizontal, vertical, and the combined resultant velocity at each moment in time. Now, what I want you to focus on at first is just the horizontal component. Notice that the horizontal component, so this is V, by the way, we should label these as V. Okay, and we can even go further and call this V initial, V1, V2, V3, and V final if we want to. And so when you're looking at just the horizontal component, which I could call Vx, V initial in the x direction, if I take a look at that initial x component to my velocity compared to the final x component of my velocity, I see that they are the same length. In fact, if I look at the horizontal component at any of these times, I see that it is exactly the same. That's because gravity can only act downward. It cannot affect this horizontal velocity. So the component in the horizontal direction stays constant, just like the picture of the ball rolling across the horizontal surface, evenly spaced. And on the other hand, though, if I look at the vertical component, I could call this, for example, V initial in the y direction. It starts off with a very large Vy component, but as gravity is accelerating this thing downward, pulling downward all the time, this component in the y direction becomes shorter as time goes on until it disappears altogether at the top of this trajectory, and then you see that after that it starts pointing downward as the object comes back down, and that the size of this downward velocity becomes larger as it proceeds in its path. Okay, and the reason for that is because all the time throughout this flight of this object, I've got gravity pulling down. The acceleration due to gravity is always the same, always pointing in the downward direction with the same amounts. This one looks a little shorter, but they're supposed to all be the same length. Okay? So the other thing to bear in mind is the angle at which I launch these things. We're not going to go too heavily into the mathematics of this since this is a conceptual physics course, but I want to point out a couple things conceptually here about the different possible launch angles. So this particular graph is assuming the same speed initially. That is the same magnitude of the overall velocity. And what do I mean by that? Let's go back a slide. So the horizontal component and the vertical component, if I do the Pythagorean theorem as we talked about before with vectors, then I get this magnitude of the overall velocity. Okay, so let's say that I start off launching things with the same overall velocity, but the thing that I change is the angle. Then I might be able to produce a graph like this of all the different possibilities for my trajectory. So what happens, say for example, if I launch something at a very steep angle, is that I've given it a very large vertical component but a very small horizontal component. And so the object will go higher due to that higher vertical component, but then it will just not go as far horizontally and land somewhere over here. It's sort of the same effect if I produce a very large horizontal component and not much of a vertical component. It can't get very high up in the air, so it's going to land not very far away from where I threw it. In fact, notice that in this example, the angle 15 degrees and the angle 15 degrees and the angle 75 degrees land in the same spot. And it is not a coincidence that these two things add up to 90 degrees. 75 plus 15 adds up to 90 degrees. Anytime you can ignore air friction and you have two possible launch angles that add up to 90 degrees, they're going to land in the same spot. So these two land in the same spot, and these two land in the same spot, and if we trace back to where those were, that's 60 degrees and 30 degrees, which also adds up to 90 degrees. So if you can, given a certain initial velocity, find something in between these extremes, then you can hope to achieve a maximal range or distance for your projectile. Ignoring air resistance, that maximal range will occur at 45 degrees. Now, of course, in the real world there is air resistance, so a more realistic value, say for a golf ball, is something like 38 degrees. Okay, a baseball is a little bit different, but anytime we can ignore air resistance, we can just say 45 degrees for our simplistic idea. Okay, another thing to note is that, again, ignoring air resistance, the time the projectile spends going up should be equal to the time the projectile spends coming down. You can also think about this in terms of energy. It started off with a lot of kinetic energy, and then it transforms that into potential energy due to gravity. It's now some height above the Earth, and then when it comes back down, it transforms that back into kinetic energy, so that when you come back down, you have the same speed and you took the same amount of time to do that. Okay, so in a nutshell, if you take a look at this clicker question, go ahead and pause the video if you like. Make sure that you understand it. Whenever you have a projectile that's represented by horizontal and vertical components, what's going to be true about the horizontal component of the velocity throughout the path of the projectile? The answer to that is that it remains the same. The vertical effect of gravity cannot influence the horizontal component, so throughout the motion, the horizontal speed remains the same. Okay. On the other hand, ignoring air resistance, if you have some projectiles, such as a baseball, moving at a high rate of speed, what is its acceleration going to be? And again, you can pause the video if you like, but it's always going to be downward at a rate of g anytime you have a projectile, and the projectile motion is defined by it just being the influence of gravity. So unless you have some rocket engine attached to your baseball, then that's the only force present, which means it's the only acceleration present, downward at a rate of approximately 10 meters per second squared. Okay, so another topic that I want to get into in this chapter is satellites, and what we're going to challenge ourselves to think about satellites is as to think of them as projectiles. So effectively what's happening is that it's a projectile that never really reaches the ground. So how can that actually occur? Well, what you've got to take into account is that for a very fast-moving projectile, the curvature of the Earth becomes important. For most projectiles we're familiar with, such as a baseball being thrown, the curvature of the Earth is completely negligible for the range that we're talking about. But if you have a projectile going fast enough that it's, say, going 8,000 meters, then that amounts to actually a vertical distance due to the curvature of the Earth, a difference of 5 meters for every 8,000 meters. So you can imagine a situation in which if you launch something with a great enough speed, you can sort of outrun this curvature of the Earth, or at least exactly match the curvature of the Earth. So take a look at this cartoon here, and it will show you 3 projectiles. One which is launched at a lower rate of speed and eventually falls back down to the Earth. Another that's launched with a greater speed, and you see that it's starting to match the curvature of the Earth. And if you can launch with a great enough speed, like this third example, then you can execute essentially a circular motion around the Earth where you're basically meeting this curvature of the Earth. Okay, in order to do that, you need to have a great enough speed, and then what's happening is that you've got the force of gravity acting on your object, and that is providing a centripetal force. So if I want to know how much speed I actually need to achieve this circular orbit, I can equate these two things to one another. When I do that, if I just say that gm1 m2 over r squared equals m1 v squared over r, where m1 is the projectile, is the mass of the projectile, and m2 then would be the mass of the Earth, I can simplify this. I notice, first of all, that the mass of the projectile actually cancels out in this calculation if I equate these two things to one another. And a power of r cancels out as well. This allows me then to take the square root of both sides of the equation, and I should find that the velocity required to achieve this circular orbit will be capital G. Remember, that's not the same as little g. That is not 10 meters per second squared. It's instead 6.67 times 10 to the minus 11. And so that's a much smaller number. That times the mass of the Earth divided by r, all underneath the square root, excuse me, will tell me the speed that I need in order to get this circular orbit. Now, r in this case is not just the radius of the Earth. It is r from wherever I am above the Earth. Let's say that I happen to be at this location. This is my r. So it is, the radius of the Earth plus this little bit wherever I'm located. That entire distance from the center of the Earth to where I'm located will tell me the r that goes in this equation. Okay, so what that's saying is that if I have a satellite which is further out, let's say now that I have an r, for example, way out here. Okay, now this r, we'll call this one r1 and r2. R2 is much greater than r1, and in this formula, if I am going to increase my denominator, that will decrease the overall number. So the satellite that's way out here is going to be moving slower than the satellite that's down here. So satellites that are close to the Earth might take something like 90 minutes to go around the Earth, but if they're at higher altitudes, they may take longer. Okay, now if you launch a satellite at an even greater speed than what we just derived here, gm over r underneath the square root, then you can actually send the satellite onto an elliptical path rather than a circular path. So what happens is you are launching the thing at a great rate of speed. It will go further and further away from the Earth, sort of like a giant projectile, which is why we're drawing this connection. And then it will start coming, quote unquote, back down or closer to the Earth, gaining speed as it goes. Okay, it will have so much speed that it will whip around and continue on this path. Okay, so as the object or satellite is close to the Earth, it will be traveling at a greater rate of speed than when it's further away from the Earth. And you can also think about that in terms of the force of gravity. As I'm closer to the Earth, I have a stronger force of gravity on me than I do when I'm further away from the Earth. Okay, so the upshot here is, in this clicker question, the speed of the satellite does what in an elliptical orbit? Well, it varies. It does not remain constant like it does in a circular orbit. Instead, as it gets close to the Earth, it gains speed, and as it gets further away from the Earth, it loses speed. Now, this leads naturally into thinking about the motion of the planets. The reason for that is that planets actually orbit in ellipses, not in perfect circles. Back in the 17th century, it took the brilliance of both Johannes Kepler's mathematical mind and Tycho Brahe's great astronomical data in order to reach this conclusion. Both of them had different ideas about how the motion of the planets actually worked, but through their combined efforts, the real nature of the planet's orbits was uncovered. Now, it's really tragic that I can't go into the history and the story about Tycho Brahe and Johannes Kepler. It's really fascinating, and so I would actually encourage you to click on this link here and watch a cool video about it where it will be discussed exactly how this came to be. But for now, I'm just going to tell you what the conclusions were. So ultimately, Johannes Kepler devised 3 laws. The first 2 came out right away. The third law took him another 10 years to devise. But the first 2 are very conceptual in nature and fairly easy to understand once you see what's going on. The first thing that Kepler was able to deduce is that rather than orbiting in perfect circles, the planets actually orbit in an oval shape, which we call an ellipse, just like these elliptical satellites that we've just been discussing. Now, the Sun is located effectively at one of the 2 foci of this ellipse. Now, what is a focus? Foci is the plural of focus. What is a focus? If you were going to draw an ellipse, you might imagine placing 2 pins and a string between them, and then taking a marker and tracing out this oval shape. These pins represent the focus. Each one is a focus of the ellipse. The further apart the pins are, the more oblong of an ellipse you would create, or the more eccentric of an ellipse you would create. The closer the pins are together, the more like a circle it will look, until if you would actually overlap the pins and just have one pin at the center, then you could trace out a circle. And so a circle could be actually thought of as a special case of an ellipse. Now, for the purposes of this discussion, this ellipse that's being depicted here is far more eccentric or oblong than the planet's orbits actually are, but that's just so that we can see what's going on. If you were to look at them, they look so much like a circle that you may not be able to tell the difference by eye, but it is true, in fact, that all of the planets in our solar system orbit the Sun in an elliptical path. The second law tells us about the speed with which they orbit. And just like the satellite going around the Earth, the planets going around the Sun will go faster when they are near the Sun and slower when they are further apart. But in doing so, the Kepler's second law tells us that the area being swept out creates an equal area in equal times. What do I mean by an area? So if I imagine an imaginary line connecting the Sun to the planet at some point in time, say at point A, and then another imaginary line connecting the Sun to the planet at point B in time, and let's say that A and B take 1 month to unfold, then I could create effectively a pizza wedge looking shape, and this shape could have some area to it that's similar to a triangular shape, but not quite, but we could compute what the area is here. Later on, let's say that the planet is now closer to the Sun, and I look at what's happening at point D of its orbit, and I imagine that same line connecting from the Sun to where the planet is located, and then 1 month later do the same thing, then what I would find is that because it's traveled further, it's traced out more of a path this direction, which means that the pizza slice I've created, instead of being long and thin like this one, is sort of short and fat, but the area inside here and here is actually the same. That's what Kepler's second law tells us. Finally, Kepler's third law quantifies things a little bit further and gives us a relationship between the period of the planet's orbit, that is, how long does it take to complete its year? For the Earth, it's 365 days. So what is the period of the orbit compared to how far away the planet is from the Sun? It turns out that if I square the period, this is proportional to the average distance to the Sun to the third power. Okay, so that's a mathematical relationship which we can see some examples of in the following planets in this chart. So Venus, being located about 72% as far away as we are, 0.72 AU, where AU is an astronomical unit. That's the average distance between the Earth and the Sun, which is why we have 1 AU. So Venus, if it's 72% of the distance that we are from the Sun, its period it takes to do 1 year is about 61.5% of our year. Meanwhile, a planet like Mars, that's about 1.5 times as far away from the Sun as what we are, is going to take 1.8 years to complete its quote-unquote year. Okay, so if you want to feel younger, you can just say your age in Martian years. If we go further out to say Saturn, which is about 9.5 times the distance that we are from the Sun, then it's going to take over 29 years, Earth years, to complete one of its orbits. Now, at the bottom of the slide, I have a link here to a Google Drive folder. I would encourage you to go to this link. What I've done there is created a spreadsheet in which you can make up your own fictitious planet in our solar system and give it some distance in Earth distances, and it will automatically compute how long its year will be. Bonus if you can explain the formula that I put into the sheet as to why this is able to compute your year. Okay, you can put your name, your fictitious planet's name, you can even name it after yourself and give it some distance from the Sun, and then it will tell you what the period is, all based upon Kepler's law, where the square of that period is going to be proportional to the average distance to the third power. Okay, now a final thing that we can think about is energy conservation as it applies to satellite motion, and this could also be thought about in terms of planetary motion as well. Sorry about that little hiccup there. What I was saying was energy conservation. So, we've already learned about kinetic energy and potential energy, and so satellites possess both of these. The satellite is moving with some speed, so it's got kinetic energy, and it's some distance away from the Earth, so it's got gravitational potential energy. We know by energy conservation that the sum of these two things has to remain the same over time. Whenever a satellite is on a circular orbit, even the individual terms are going to be the same because the potential energy isn't changing, the kinetic energy isn't changing since it's moving at a constant speed, and so the sum of these two things will be the same at every point in time, and the individual things will also be the same. Now, if you have an elliptical orbit, the sum of the things has to still be the same, right? The sum of my kinetic and potential energy still has to stay the same by energy conservation, but the individual terms are going to be different. When I'm close to the Earth and I have all that speed, I've got lots of kinetic energy, but not as much potential energy because I'm close to the Earth. If I go further away and I'm way out here, then I have a less amount of kinetic energy, but lots of potential energy due to my distance away. And somewhere in between, I've got a medium amount of both. But at every point in time, if I add these two things up, the sum will remain the same throughout. And finally, if we get enough speed, we can hope to potentially outrun the gravitational influence of the Earth and not actually orbit it at all. This is what we would call escape speed. It's important to note that you don't technically ever escape the gravitational field of the Earth. And yet we can actually achieve what we call escape speed and not continue to on an orbit around the Earth. You're getting away from it fast enough that you can continue forward. And I won't derive it, but the formula for calculating escape speed in general is going to be very similar to the one we saw for a circular orbit. The only difference here is a factor of square root of 2. Okay, so if I multiply that orbital speed that we had for a circular orbit, gm over r, by square root of 2, I will achieve escape speed. This is a general equation that I could use for any massive object. For the Earth, I would plug in the Earth's mass and radius, and I would find that when I launch, if I want to escape, I need a speed of 17 kilometers per second, which is equivalent to 7 miles per second. If I'm on a less massive body, such as the Moon, I won't need quite as much speed. I need something like 2.4 kilometers per second, which is equivalent to about 1.5 miles per second. I'm not expecting you to memorize these things, but suffice to say that with a little bit of speed, we can achieve this circular orbit. More speed, we can go on an elliptical path. Even more speed, and we can escape and perhaps go to other worlds. Now, as I said, though, you're not actually escaping the force of gravity. We learned that the gravitational force is proportional to 1 over r squared, or 1 over the distance squared, and so you would have to technically plug in infinity to get this to equal to 0. That's all I have for today. Next time we will start talking about Chapter 11. Thank you.